as usual, let me begin with a summary from the previous week. The main discussion from the last week was about the rational function fields. Particularly, we consider two types of discrete valuation rings. One is determined by an irreducible polynomial p of x, and the other one is denoted by the O infinity. We will also say that the place is at infinity. And for these valuation rings and the corresponding places, we define the residue class field. We have observed that in these cases, we have two types of residue class field. For the first case, we have seen that this is isomorphic quotient field k of x modulo the ideal determined by the irreducible polynomial p of x. And in the second case, we have observed that residue class field is isomorphic to K. And as an important conclusion, we will say that the place at infinity is a rational place in the rational function field K of x. And particularly for degree found places, so I mean for the rational places, depending on these types, we determined the residue class maps, particularly their images. In the first type, we observed that the images is determined by the evaluation of the function at a given point. I made a mistake here. Set of AI. And in the second case, it works some sense the limit of the fractions. And depending on the degree of the f and g, we can find the evaluation of the function, rational function z at infinity. So about the rational function field, it's quite natural to ask, do we have other type places or the discrete valuation rings in this example? So this week, particularly in this lecture, we will answer this question negatively. So that means these are the only places in the rational function field. And here, let me also observe that since we have infinitely many irreducible polynomials in the polynomial ring, we can also conclude that indeed there are infinitely many places in the rational function field. So generally, we will also answer this question in a similar way. And we will observe that there are infinitely many places in a given algebraic function field. And we conclude this infinitude of places as a consequence of what is called with weak approximation theorem. But since the theorem is a bit technical, particularly its proof is technical, in the second video record of this lecture, I want to give some motivation, particularly regarding the Lagrange interpolation, which is a quite strong tool, particularly in applications. So, okay, in this video, now let me prove that in the rational function fields, we can only have two types of places, which is either determined by an irreducible polynomial p of x, or rational place P infinity. And in order to prove that, let me consider a place in the rational function field Q of x, and let me also consider the corresponding valuation ring OP, and for the brevity, I'm going to denote it by simply O. And for the transcendental x, since we have only two cases, so that means it can be an element in O or it's not in O, we will prove it regarding these two cases. And in the first case, so if the transcendental is an element in this discrete valuation ring, we know that the polynomial ring with the indeterminate x lies in OP. And now let me set the ideal Q of x intersection P, which is a proper ideal in the polynomial ring Q of x. And here my claim is that, our claim is that A is indeed a prime ideal. So that means first we need to see that A is ideal, and please check it. And to see that, to see that it is a prime ideal, so that means if the multiplication of x and y, two elements, two polynomials lies in O, then x in O or y in O, one of the elements should be lies in P. And in order to see that, this is our claim. Let me suppose multiplication in P and one of the elements without loss of generality, x not in P. And by using the correspondence of the places and the discrete valuation maps, we can represent this statement as Vp of x pi is strictly bigger than 0, and Vp of x strictly less than 0. And by applying the properties of the discrete valuation map, we can see that if this sum is positive, even though the Vp of x is negative, then this forces Vp of y should be positive. So y should have 0 at P. And this shows us y in P, and we can conclude that A is prime ideal. And since we are in the principal ideal domain, but before that, the other claim is that if we consider the ideal, proper ideal in Q of x, which is determined by the polynomial ring Q of x and the intersection P, the first question is that this ideal can be trivial. And towards the contradiction, let me suppose that it is trivial, but in this case, since the residue class map induces an injective from this quotient to the residue class field, and in the previous lecture, since we show it is finite, we can get an inclusion because in this case, the K of x is infinite dimensional vector space over K. So there is no way to embed an infinite dimensional vector space inside the finite dimensional vector space. And this shows us I should be trivial. And since we are in the principal ideal domain, any prime ideal is also maximal ideal, and we can guarantee that there exists a monic irreducible polynomial which generates the ideal I. Now our claim is that the corresponding valuation ring indeed is the same valuation ring which is determined by the irreducible polynomial p of x. And to show the equality, it's enough to observe that, it's enough to see that this valuation ring lies in OP, because as we have seen before, every valuation ring is a maximal proper subring. So OPX is maximal proper subring. And by the maximality of PX, we get the equality. And to see this inclusion, let's consider a fraction f over g in OPX. So that means g of x is not divisible by p of x. And this condition also tells us g of x cannot be element in P. Because if g of x in P, g of x also should be in the ideal, which is generated by p of x, and in this case, p of x divides g of x. And by the correspondence between the places and discrete valuation rings, if a polynomial is not in P, we know that its inverse lies in the corresponding valuation ring OP. On the other hand, since f of x is a polynomial and the polynomial ring contained in OP, by the restructure of a discrete valuation ring, we can see that this fraction is also element in OP. And this shows us this inclusion. Now, as a second case, if the transcendental x is not in OP, again by using the correspondence between the valuations and places, we know that its inverse lies in P. And in this case, the polynomial ring with indeterminate x inverse lies in the valuation ring OP. And similarly, in the previous case, let me set the ideal as an intersection of this place and the polynomial ring K of x inverse. And indeed, this is also prime ideal. And my claim is that it is generated by the irreducible, linear irreducible x inverse in the polynomial ring K of x inverse. And to see this inclusion, before keeping doing this proof, let me prove this equality. Obviously, x inverse lies in this intersection because this is a linear polynomial here, and we suppose that x inverse in P. And this shows the right inclusion. And for the left inclusion, since P intersection K inverse is prime ideal, and you can prove it. Please check it as I proved. Here, for the first case, then we know that it is generated by a monic irreducible polynomial P of X inverse. And in this case, if we are able to show that this monic irreducible polynomial indeed the polynomial X inverse, we will see the equality. And to see this, suppose not. Indeed, I think maybe it's enough to only considering this proof, we can simply show the equality, but let me follow in this way. So let me suppose the monic irreducible P of X is different by the X inverse. So, and since both of them are irreducible, their greatest common divisor will be 1. So that means by the Bezier identity, we can guarantee the existence of the polynomials A and B such that A times P plus B times X inverse is equal to 1. Since Px inverse is a generator of the ideal, this multiplication lies in the ideal I. And on the other hand, X inverse, we have seen that X inverse in this ideal, this multiplication also lies in I, but A is a proper ideal in the polynomial ring Q of X, and this gives us contradiction because this ideal cannot contain a unit, particularly 1. And by this observation, like in the first case, our claim is that if X is not in OP, then OP is indeed the evaluation ring O infinity. And to prove this, from one of your homework questions, let me use the notation for O 1 over X. And again, it's enough to consider one inclusion because by the maximality of O infinity, we can conclude the equality. And for this inclusion, let me consider a fraction from this valuation ring, so that means X inverse does not divide the denominator G of X inverse. So that means G of X inverse is not in P, because otherwise, if it is an element in this ideal, X inverse divides Gx inverse. And again, by the corresponding places and the discrete valuation ring, we see that its inverse lies in OP, and on the other hand, the polynomial ring also lies in OP. We see that this multiplication for such an element is also element OP. And since these are the only cases we can consider, we can conclude that we only have two types of places in the rational function field Q of x.